Hello students. So in the last set of videos we talked about locating, how to position the part correctly. And we're going to get to clamping, which is the next part of that. Once you locate it, you clamp opposite those locators. But first we're going to talk about inspection and gauging, because often gauges may or may not have clamping. It just depends. Sometimes it's really helpful to be able to clamp the part in place, but sometimes you just put a part into a gauge and you measure it. And it's a really similar topic to locating, because determinism is so important when we're doing an inspection type process. So we're going to go ahead and move forward with this. Whoops. Sorry. There we go. I reappeared again. Okay. So one thing I want to talk about first is just make sure that we're all talking through numbers correctly again. It's been a long time since you were in 332, and so you may have forgotten the nomenclature that's commonly used on shop floors in the US customary system. So just to make sure, this number right here is, if you remember, 1/1000th of an inch, or you can call it 1 thou. Some people will call it 1 mil, but I want to really discourage you from doing that, because people also call 1 millimeter 1 mil, and then that gets really messy and people don't know what they're talking about, and a millimeter is hugely different from 1/1000th of an inch. And I want you to remember, when you're thinking about this and trying to think about, well, what is 1/1000th of an inch? Paper is about 3.5 thousandths thick. It depends, of course, on the weight of paper that you get, but it's, on that order of 3 to 4 thousandths generally. Okay, this number, 0.010, remember we continue to talk in thousandths, and so this is 10 thousandths of an inch. And so we will continue to talk in thousandths. Now, it would be easy to think that this is 1/100th of an inch, and I mean, technically it is, but that is not the way it's talked about on the shop floor. This is 10 thousandths of an inch. And this one, where you could call it 1/10th, and that would be correct mathematically, on the shop floor, this is 100 thousandths. You continue to talk in thousandths as long as you're larger than 1/1000th of an inch. And so there you go. 1/1000ths, 10 thousandths, 100 thousandths. Okay, this number, 0.0001, is less than 1/1000th, and this is called 1/10th, or 1/10,000ths of an inch. Okay, so this is why we don't call the previous number 1/10th of an inch. It's because 1/10th is reserved in the way that is commonly talked about for 1/10,000ths of an inch. Okay, so when we're thinking of things, 1/1000th of an inch is 1/3 or 1/4 the thickness of a sheet of paper. 10 thousandths of an inch is about the thickness of 2 or 2.5 sheets of paper, somewhere in there. 100 thousandths is nearly 1/8 of an inch, and so that is a pretty big measurement. You know, that's half of a 1/4 inch, so it's pretty big. And 1/10th of an inch, 1/10,000ths, is a really small amount. So many CNC machine tools, just your standard run-of-the-mill machine tool, might have a positioning accuracy on the order of 1 to a few 10 thousandths of an inch. The cutting accuracy generally won't be quite that good because of tool deflection and any loose joints that there are in the tool body makeup or anything like that. But anyway, 1/10th or 1/10,000ths of an inch is a really tight tolerance. Now, a precision machining process can make 1/10,000ths of an inch, but a 10 thousandths of an inch is pretty small. So you should think of that if you're calling out tolerances or dimensions to 10 thousandths of an inch. Know that it's going to cost you a reasonable amount of money to get it. And it probably, depending on what it is, might be able to be done on a normal machine tool or might require a higher end or precision machine tool. Okay, just to be finicky, 0.00001. You could look at this and think, well, that's 1/100th or something. But in fact, when you get to this many decimal places, we start to refer to the numbers in millionths. And so this is 10 millionths of an inch. And if you are operating in that realm, you can also call this number, what we called 1/10,000th of an inch or 1/10th, can be 100 millionths if you operate in that realm of numbers. And if you are operating in that realm, that means you have a special machine tool that has the ability to machine in that area. Generally, folks don't spend much time there. Okay, so metrology, remember, is the study of weights and measures. It means to measure or to study your measurements. And so there are we're only going to be talking about the measurement of lengths in this class. We're not talking about volts or amps or any of the other really cool things that you can measure when you do metrology. We're just doing length measurements. And there are sort of two main camps of how you measure things. One is a gauge and one is a measurement fixture as related to this class. So in a gauge, all we're doing is checking a few related features. We're not checking the whole part, and we're generally only checking the tolerance limits. So it's a go, no-go kind of a decision. We're not measuring what measurement did we get. We're just saying, yes, it complies, or no, it doesn't comply. They're very robust. You can use them on the shop floor, so they're great for that. But they don't help you do any statistical process control, right? All that stuff that you learned in quality assessment. This isn't helping us to generate any data. We aren't improving our process. We aren't getting closer to our targets with any of this. We're just finding out what rate of things we're scrapping, and that's all we know. So to get that kind of information, we go to a measurement fixture. And a measurement fixture allows us to position the part really precisely and then actually measure the features. But measurements take a lot longer than gauging does, and so we don't want to have to do that all the time. Okay, so lots of different kinds of basic metrology gauges. You can have a plug gauge where you're putting it into a hole, and generally we would have a go and a no-go. So one end would fit, the other end wouldn't fit. We would find out that it was the right size but not too small. You can also find out if it's too big to some extent. We can have ring gauges to find out if a shaft is the right size. Again, generally we would have a go and a no-go set. We can use snap gauges like this. So this takes a shaft and you slide the shaft in. We would be looking at the end of the shaft, and it should fit between the first two anvils. That's the go, and it should not fit between the next two anvils. That would tell us that the shaft is undersized if it fits through there. And then there are all kinds of other neat ways that you can create gauges. So this is an example of a flush pin gauge. So this is for measuring the chamfer at the top of a hole. So it has a ball that is glued to a stick, and on the end of the stick is a little step. And so to be in tolerance, you have to be, the top end of the stick has to be protruding from the end of the gauge, but the bottom end of the stick cannot be protruding from the gauge. And so this gives you a go, no go sort of measurement. So there are all kinds of these. The fixed limit gauges are for measuring slots. One of these will go in the slot, one of them won't. Again, a go, no go kind of thing. But then there are other ways that we also gauge things. And so I want to show you this on this gauge that we have here. Oh, look at that, technology. So on this gauge, we looked at this a little bit in the last lecture, but what I've done is set this up with 3 points on the A datum. So I'm taking the A datum is this big flat area here, and I've set up 3 locators, and then I've put 2 locators on the B datum and 1 locator on the C datum. And so by those 3, these 3 have eliminated 3 degrees of freedom. These 2 on the edge have eliminated 2 more degrees of freedom. I'm up to 5. And then this last one eliminates the rotational degree of freedom, so then I'm at 6 degrees of freedom limited, and so I can go ahead and check it. And so the way that a gauge like this might work is you can see there are other holes in here, and they're labeled gauge, which I'm sure you can't read, but anyway, they are labeled gauge. And so I would take my part and I would set it on the A datum first, and then I would slide it against the B datum next, and I can't let it come off any of these datums that it's on. So I have to keep it down on the A datum, I have to slide it against the B datum, and then slide across the B datum to the C right there. And then what I would do is, if I'm checking like the true position of these 3 holes, then I would take this gauge pen and I would drop this gauge pen in and see if it goes in the hole in the gauge down below. And it's a little hard to tell, but if I move this off the B datum, oh, come on. Anyway, if I move it a little bit off the B datum, I see that it falls in the hole. And so this part, and I can check the other holes, right? So I'm holding it on A, B, and C. I check this hole, and it goes, I think it went all the way down. Yeah, it went all the way down in that hole. And I checked that one, and it did not go down. And I'm not actually sure that I can move it enough to get it to go down in this hole. Okay. Well, yeah, anyway. So it's not going down. So this part would fail, right? Now, I only have to do these one at a time because these are called out individually. I could also check the true position of this center hole by using this big plug, and you'll see that I can't, in fact, do that. This hole was intentionally made to be off-center or at an angle, and so if I put it on there, you can see that I can get the whole thing to go together. But if you were here and could see it, maybe I can pull it out carefully. Did you see that? The whole part falls down, click, and falls back in. So this hole would not pass a test of a number of things. It might be a true position, it might be a cylindricity, or yeah, it might be a parallelism to one of the sides. This hole up here would not pass a true position test. And so this is just a pretty simple gauge, right? So I could have this down on the shop floor. Somebody can put the part in there, hold it in place, or even better than that, I would have just a clamp that comes in and holds it in place once they get it there. And they would come along and drop those pins in and go, yep, okay, that hole's good. This hole may actually be good. I'm not, no, it isn't. And then that one, it would be good too. Now the reason that they're not working is that I put this pin in upside down, so it's the wrong length. And I did that on purpose to make the A datum be tilted so that some of those would measure out. Otherwise, this part is in fact good. Okay, so that's just one example of a kind of gauge that could be used. And there are lots of different types of gauges that could be built, but this is just one kind. And so we're going to be working in class to understand how to tolerance gauges, and then also you are going to be designing a gauge to in fact check several different features. Now notice with that the results are totally different if my A datum were the center cylinder rather than the flat on the bottom side. And so if that were the case, I would assemble the gauge differently and position things differently, and the results might be different for those parts as well. Okay, so I'll see you in the next video when we'll talk about how to tolerance a gauge.